Oh my. For the people. Oh. We do it for the people. What are you trying to do? You just want to turn to your left? Not an end, but turn a. Someone joined us. Someone joined us. Who's that? I wonder why it brought that. Hi. Yeah, sure. So, energy is, especially if we're doing this, energy is always conserved, right? I'm actually going to turn the music down a little bit. It's hard for me to concentrate. so if we're talking conservation of energy, right? Generally, we're talking about something in physical motion, right? So if we are, generally we've got like a physical object that's in space somewhere, right? We speak of it having a kind of total energy, which is potential energy plus kinetic energy, right? And this is preserved through motion. So basically, it's got kind of a total amount, and whatever that is always preserved unless preserved through motion. The only exception is if work is done on the object, on or by the object. Because work is also energy as well, right? So you'll often see this in cases where you've got the biggest potential. You've got two kinds of potential energy, right? The two kinds are, of course, gravitational. Which is the mass of the object times gravity times the height. And then you've got spring. I think that's pretty much the only two you have to deal with. And even though, like, even that, I'm not sure you have to deal with spring that much. Spring should be 1/2 kx squared. With me so far? So yeah, so that's the setup. And if you've got a problem like that, what you want to do is kind of go through and think of the sources at the start, right? Before anything has happened, what are the sources of energy that this object might possess, right? And calculate what that is. Usually it's pretty simple. It's either the object is standing still or it's moving, right? If it's standing still, then you're dealing with some kind of potential energy. And if it's moving, then you got some kind of kinetic energy. So the one you always bring up is... Nope, not that one. You've got the bullet that hits the pendulum, right? And so basically, we've got the system where this has 0 total mechanical energy. I think that's the phrase they use. And this has some kinetic energy. Right? So let's say, what's a good speed for a bullet? 50 meters a second? So bullets are usually like small, so we'd say something like, oh, I don't know, 0.1 kilograms. That's actually pretty large for a bullet. Let's make it 0.01 kilograms, right? And then you've got, I don't know, it's going 200 meters a second, right? I don't know, I'm just making this up. I'm just trying to see what's reasonable for a bullet. And so you find the kinetic energy, it's 1/2 0.01 kilograms. It's a very heavy bullet. Times 200 squared, right? 200. So that's like 200 joules. If I'm doing my math right, which I may not be, but I think I am. And then when it hits this, like, you know, once it hits this, say this has a mass of, I don't know, 1 kilogram. Most of the times, if we're thinking bullet's going to stick in, so chunk, right? If it sticks in, all that kinetic energy becomes possessed by this system, this pendulum system. And it's like, a common answer is like, how high is this pendulum going to go, right? Well, if it's going to its maximum height, all of this kinetic energy has been changed into potential energy. So you're like, oh, we have this kinetic energy, 200 joules. This is the only source that's from the bullet. That equals mgh. And the only real trick here, we know what g is, it's around 10. The only trick is to, you know, keep in track that the bullet plus the weight is now our new mass. So you've got 200 joules equals 1.01 times 10 times h, and a simple division to find out what you got. Does that seem reasonable? And then you got other complications like, I don't know, no, energy is never lost unless work is done. So in an inelastic condition, so yeah, that's an inelastic collision. So the energy is lost by the bullet. So this is a trick, right? So you're so it's like so yes, energy is lost. You're right, it is an inelastic condition, right? Is lost. What is it lost by? It's lost from the bullet. I don't know why this is better at the top of the thing than at the bottom. So yes, the bullet loses energy, but at the total amount of energy in the system stays the same, right? Before and after the collision, like before the collision, you have two objects. After the collision, since it's completely inelastic, you have one object. Right? So yes, the bullet loses kinetic energy into the pendulum, but the bullet and the pendulum are stuck together, and there's a finite amount of energy that's available to them, right? If we were worried about just the bullet by itself, then yeah, but that's kind of a silly thing to think about, because now the bullet is stuck in the pendulum, right? Still, like, yeah, so it's a fine detail, right? Total mechanical energy cannot be lost unless work is done on the system, like through friction or something, right? But you're right. In an inelastic collision, the kinetic energy is lost, but it's lost from the bullet, and it goes into the pendulum. I mean, you could also say that it's lost to like heat from the collision, which is true. We in this case we kind of idealize, we hand wave that. Does that seem like a reasonable thing? And I only picked that example because I'd heard you complaining about it in class. The Doppler effect. Okay. So do you need to just talk about it, or do you need to like actually do calculations with the Doppler effect? Ugh. All right, well, I mean, I'm not sure you heard the question, but all right, Doppler effect. That's fine. Let's just talk about the Doppler effect. So say you have an object that is creating sound. So you've got an object that's creating sound, and sound is a pressure wave, right? So you have, you can imagine these waves coming out from the object, right? And they come out at regular intervals, right? So there's two equivalent, but you know, kind of slightly different cases of the Doppler effect. One is if you have a moving object, and that's pretty easy to like think about. Like, so if this object is moving, right? Well, once it makes the sound waves are emitted from wherever the object is at that time. So you have this case where the object makes, you know, if this is the object's motion, it makes a sound wave here, then it makes a sound wave here, and then here, and then here, and then here. So when you look at that stacked up, the direction, the sound waves are going to be closer in the direction of motion because the object has kind of caught up to it. And they're going to be farther away in the direction that's not the direction of motion. Yeah. Sorry about that. Right? So over here you have a higher frequency. If you are in the direction that the thing is going to be motion, and over here you have a lower frequency. So of course in sound, this is the characteristic siren coming toward you, like, right? So when you're in front of it, you get this high pitch thing, and then as soon as it passes you, it gets lower than what the true frequency is. And now, like, when you're talking about, like, oh, a lot of these questions that might be asked about the Doppler effect are qualitative, right? Where you're like, oh, you are here, what's the frequency compared to something like that? Key thing to remember, if you are exactly... If you're exactly perpendicular to the moving object at the point we're interested in, so if you are like here, or here, you hear, like, if you're in either of these points, you get the true frequency, which is the frequency that the object thinks it's emitting, right? Oh, fancy formulas. Okay. Well, let's see. What would the fancy formulas have to be? Yeah, Doppler effect, that's one of the things that's going to be a little bit more common with as qualitative questions rather than quantitative questions. like being able to see like, oh, if you're in this part, you have higher frequency. If you're in this part, you have lower frequency, right? It's kind of like a wave thing. In terms of the fancy formulas, and I'm sure there are fancy formulas for calculating how much the frequency is shifted. Let's see if we can do this. Common things. So just remember, if you're asked to do calculations, right? And I don't know what the formula is off the top of my head, but I'm sure there is a fancy formula. You want to have like the relative. You want to find. You want to know what the speed of the wave is. So it's typically sound. There is Doppler effect for light, which are the two big waves you have to worry about. You'll probably won't calculate. So if you're calculating, it's probably sound. Right? So I'll put it, if it's right, you need to know that this is sometimes known as blue shifting. Because higher frequencies of light, if we're talking in the visible spectrum, you got a higher frequency of light, it shifts more. Oh, that doesn't look like shifting, does it? It is closer to the blue end. And if we're talking about light, this is called red shifting. And I may have to. Which is fun. Yeah, that's gross. So you need to know the speed of the wave, and you need to know the relative speed. So the speed. All right. Excuse me. Arthur's being a little fussy right now. Because we're getting near this fussing hour. Excuse me while I stand up and bounce him a little. It's not quite there. So I've got a physics book right here. I can look up the fancy formula. Again, concentrate more on the qualitative in this case, because that's more likely what you're going to be asked. Let's see. What is the Is there any optics on Physics 1? That seems like weird that there isn't, but I guess that makes sense. Oh, my physics supposed to cover this. Okay. Orbital speed with radius and speed of a planet in space. That's one of Kepler's laws, isn't it? Let's see. Square period is proportionally q to the semi-major axis. Maybe? Yeah. Let's see. Orbital period. There's probably a couple ways to calculate that. Radius and speed of a planet. So, square of a period is proportional to the cube of the semi-major axis. So, but you need to know what the rotational, well, I mean, you can find the gravitational force. You have K gravitational attraction, and then M1, M2 over R squared, right? And that's always, yeah, sorry, it's hard for me to draw. That force is always perpendicular to the motion, and then you have your rotational motion equations, right? Yeah. With radius and speed of planet in space. Kepler's laws. So we got the period, square of the period is proportional to the cube of the semi-major axis. We also have the square of the period is equal to k times the cube of, we're talking circular, it's the radius. Oops. Either could probably be used, because it all works the same. Let's see, where... Let's look up circular orbits, because why not? I'm sure there's fancy v squared over r. Square root of gm over r, yeah. There's a special one, like if we're in the business of memorizing equations, which I guess we are, since we can just put them in a calculator. When you go through a bunch of stuff, the velocity of the orbiting body is the square root of big G, it's a gravitational constant, m over r. This m is technically mass of both. But if we're talking orbital things, unless you're doing something weird, we, make it both and just use the bigger mass one. Right? I mean, I'm not going to stop you. Relate orbital period with radius and speed. And so, I mean, so if you want to talk about orbital period, so of course we have this that relates orbital period with radius. So if we want to bring speed into the equation, I guess we could like tie this in with this if you feel like it. Oh, but that makes sense, yeah. Since if you know the radius, the period is going to be the time it takes to make one full rotation. So it's going to be the distance divided by the speed. So it's going to be 2 pi r over v. But yeah, you can ask a calculus question. Go ahead. All right. Take your time. I'm just chilling. I mean, Arthur has quieted down. I hope he hasn't settled into a nap because his bedtime is very soon to now, but, I hope I didn't scare him off. I'm kind of surprised that Arthur fell asleep like this, but it is what it is. Check. Oh yeah. Hi, bub. And just as a final thing, this equation that we have for period, if you need equations for period, this equation that we have will work for, like, this isn't just, so this is any rotational motion. Obviously, the velocity isn't always going to be derived with this, but you know, if you have any rotational motion, then that's going to be it. The work done by friction, oscillating horizontally with friction. That. So friction resists motion. Okay. Oscillating horizontally, get work done by friction. Over how much time? I guess it doesn't particularly matter that much. Okay, so you've got something oscillating. So nope. There we go. So let's see. Oscillating with friction means we've got like thing on the floor and it's connected by a spring to something, right? Friction always opposes motion, and friction is of course mu times F normal. So if we're moving, make sure this is kinetic. And then, you know, work is of course always the dot product of the force times the displacement. Luckily, this is pretty easily figured out. So are we, this isn't necessarily a question I can answer in general. So those are, sorry, I'll get back to that. So all the things that might be related. So work is force times displacement, and of course, if we have a spring, we want spring kinetic energy. Kx squared. So, like, once I've got those equations laid out, and these are just kind of the general things that we know about this, it ceases to be a problem I can do in general because I really need to know what the specifics are. Whether this is x equals 50, m equals 2 kilograms, spring constant is that. Okay, so that's where it begins. So that's a good start. So let's make sure that we got the start. So the kinetic energy in the system, 50 to Newton meters. So you have x equals 50 centimeters, k equals 100 newtons per meter. So we'll change this. This is, of course, 50 centimeters, which is half a meter. So the starting spring kinetic energy, or sorry, string potential energy. The starting potential energy in the system is going to be 1/2 times 100 times 0.5 squared. 50. So that's like 12.5 newtons. And then, are we bringing it to a stop? Because like this is how much we start with, and of course the mass is going to be important later. But you guess. So work done by friction. So what I'm missing from this is some kind of measure of the distance that this is going to travel in its oscillations. So either you could release it, because of course it'd be nice to compute the force of friction. That'd be easy, except it doesn't, like, your problem doesn't really detail the mu. So we can't really, the force of friction is kind of a mystery at this point, right? But that's, not the worst thing in the world. If we knew something else about, like, basically, we could answer this if we knew if there was a final, like if we had an x final. It could be positive or negative. It doesn't actually matter, because then we could find the spring potential energy, like if it came to a stop, which under friction it would have to come to a stop, right? So you'd release it and go back and forth and back and forth and back and forth, and eventually it come to a stop. If I could tell where that stop was, we could find the potential energy at the stop and then just find the difference, right? But as it is now, this is not a solvable problem, I want to say. Because we have, like, you haven't given me something that's specific to a problem. I'm guessing it is something like where you have a final position and you can just take the difference between the spring potential of one spot and the spring potential of another spot. And whatever that difference is, that's the work done by friction. That seems most likely. Part of the surface has friction and part doesn't. The last 30 centimeters does. Yeah, this would be a lot easier if you could like just send me a full picture, which I guess you could do. You have an email address, which is open right now. So if you sent a picture to that email address that I sent the notice email to, like I'd get it. But yeah, if you want to just move on, that's fine too. The work done by the frictionless surface. Yeah, there wouldn't really be an opportunity for a frictionless surface to do work on an object. I'm trying to think of an exception, but there really isn't. But yeah, if it's horizontally oscillating, and you're asking about the work done by the frictionless surface, it has to be zero because there's no other opportunity for it to do work. Electric fields. All right. So charges emit electric fields. Charges emit electric fields. You can talk about the attraction. So the force of attraction between charges. Let's do electric. I don't know. There's a specific constant which I forget at the moment, but it's the charge on one times the charge on the other over the distance between them squared. This may look familiar because it's the same as the gravitational attractive constant. So you've got that. You probably also, so that's if you have two charges, and most of it all kind of like does it with that. You also can have charges motion in an electric field. Or the work done by a charge to move through an electric field. Usually, we don't talk about like uniform electric fields or anything. Capacitors and dielectrics. Right? Let's see. Do you have to talk about electric potential? Or potential difference in a uniform electric field? Or Gauss's law? Probably not Gauss's law. Yeah, you're not talking about flux. So yeah, let's see, what are the big ones? Net force of an electric field. Oh, cool. So that's if we're talking point charges, the electric field. All right, so net force. So we kind of test for electric force. So you have like the electric field vector, which is I'm going to do that. We usually test it with the force on a test charge divided by the actual charge. It's important that we note that this is on a positive charge. So we kind of like so if you want to rearrange this and you're interested in like the force, so the force on a charge is going to be the strength of the charge times the electric field vector. And of course, and then I guess the signs match, right? So if your charge is positive, then you don't have to worry anything. If the charge is negative, then it's going to switch up and be in the opposite direction from where you're looking at. In terms of units, it's good to know that this is, no, not this. This is newtons per coulomb, which is all nice. So let's see what. You need to find like do you need to find like the no, because it's force like force is always on a thing. Do you need to find like electric field strength given off by something? If the points are in a triangle. Okay. Okay. Well, that's very specific. Like that kind of triangle, an equilateral. Like this is the kind of thing where specifics are appreciated. Because again, like if we're talking 3 points, and like this is the point that we're focusing on, like for whatever reason, which I'll draw I guess, right? This has a force like of between this guy, and it has a force between this guy, and then we have to do some trig to find net force. Like generally you're gonna any triangle not equilateral. You're gonna have to do some trigonometry. Like I mean, in general, you're just gonna have to do some trigonometry. And if it's just 3 points, that's not the biggest deal. But yeah, so I would use yeah, so like use this for the appropriate constant. I forget what it is. To to find the force here and the force here, or in whatever case, right? Maybe it's like this. So like you always have like one that you're looking at, and you want this force and this force, right? In that case, and then you'd find the net force wherever that might be. So it might be this. Divide it by the charge, and that'll get you your electric field strength. Let's see, are there any? No, that's a dipole. You probably don't have continuous charge distribution. Chances are low, because that requires a little bit of calculus. I'm going to send you a picture. Yeah, that in this case, especially with something this visual, it's a lot easier. My apologies that we couldn't communicate this through text. Three particles are fixed in place. If the charge goes into that. Okay. This one, 10 minutes. Four. Four times 10 minutes. Okay, 7 times 10 minutes. Q1, Q2. Oh. Okay. Electrostatic field force, we got that. Determine the sign of the charges. Alright. You with me? You're with me. Nice. Probably. Alright, so first of all, we want to determine these signs, whether they're positive or negative. And in this case, that's fairly easy to do. This is a positive charge. So if the net force is going to be in this way, this one's pretty much has to be negative so that you have an attractive force. Now, the question becomes what this is. If this is purely in that direction, then that oh, so that has to be 53. So magnitude of that. I'm just trying to decide, by the way, now. Like, it makes most sense for this to be positive so that it is a repulsive force. And it's like that. I just have to make sure that it all balances so that we only have it in the x direction. So let's see. If we're talking this is our force, the actual attractive force between Q1 and Q2. Between Q1 and Q3 in the y direction. For K 1/4, so 53. Oh, I guess we could use that. That's a 3, 4, 5. Yeah. Whichever. The force of this in the y is going to be wait, that's not 53. That's 37. 37. I'm an idiot. I'm not an idiot. I just this is hard. And so basically these have to be exact opposites of each other in order for this to balance out. And so from that you should be able to find out whether it's a positive or negative. Oh wait, no, right, duh. This has to be positive. So that's the opposite. Otherwise it'd bend further. Alright, that took a while. Sorry that took a while. So that's the first part, is find whether it's negative or positive. And if you don't get bogged down, most of this is actually trash. We may need it later, but for right now it's trash. Go back to components. Always go back to components, right? This force vector, which has to be this way, we have a portion this way and a portion this way. The only way to cancel out this portion is if this is a repulsive force instead of an attractive force. Otherwise the force vector would be pressing inwards. So of course Q1 is negative, Q2 is positive. So on the diagram, draw force 1 of the force exerted by particle 1 and particle 3, and the force exerted by particle 2 on particle. Oh, I kind of already did that. So this is, I mean, not quite. This is the force of particle 1 on particle 3. And then technically you want to do this is going to be the force exerted by particle 2 on particle 3. Drawing clearly, label clearly where another positively charged particle can be placed in the net electrostatic force on particle 3. And particle 3 is 0. Another positively charged. The net? Oh, if you want the net to be 0 and you have a positively charged, since this is positively charged, you just put it, the net force, like if the net force is already on this line, you put your other positively charged thing on this line, and then you don't have to worry about all of this anyway, so it's fine. Oh, calculate the magnitude. Oops, I missed that one. The electrostatic force on particle 3. Well, if we know these exactly balance out, we can kind of forget them. So it's going to be so we want the this component of this one and this component of this one. So we're going to want the net oh, it's hard to write on this part of the pad. We're going to have this one except for cosine. So we're going to K. You should probably have the coulombs, so it's 1 times 10 to the negative 6 times 4 times 10 to the negative 6. Over 4 meters squared, so 16 squared, 16 square meters, times, since we want that component, that's going to be cosine of 37. And then we have to add this one. So, and just make these positive. Since we're looking for the magnitude, just make it all positive. Times 10 to the negative 6 times 1.7 times 10 to the negative 6 all over 9. These are clean ones. Whatever. Times the cosine of, in that case, 53. So that was a lot. That was a whole lot. How are we feeling about that? Yeah, it is kind of annoying, but again, fall back on what you have to know from your trigonometry, and don't be afraid to just kind of like any vector you can easily draw. Make sure to decompose it into x and y coordinates and see where they have to balance. Hey, bub. How you doing? What? Ah, okay. On a pulley with one on the ramp, how do you derive the acceleration? Yeah, of course, with friction. Oh, it just wouldn't be the same without friction. So you got a ramp. Typically, it's looking something like this, where you got a block on the ramp, and you got a pulley, and then you got, and typically it's, I guess, a little bit farther, and then you got another block, right? So we call this M1, and we call this M2, right? So the biggest problem is that, oh, hey, buddy. So You want to find the force. This one, the force is easy. Of course, this is F equals m times g. Technical difficulties. I didn't get to use my technical difficulty sign, but we'll get to that. This one is trickier, of course. You're going to need to know, typically they give you this angle. So of course we have the total force on this, that the force due to gravity. You're going to have to decompose this into this correspondence and this correspondence, where this is balanced by the normal force. So the force of the normal is going to be m2g times the cosine of theta. And then you have this, the force that's parallel to the side, so that's going to be m2g sine of theta. Right, and this force and this force are going to oppose each other. So you're going to have to find out, essentially, which one wins. A little bit. I mean, you don't technically have to. Or, yes, you do have to. So you find the force net on the kind of system. It's weird. And that is going to be, you know, the parallel force, or the difference between the parallel force and the force on mass 2. This is before friction. Right? So that's the, because friction kind of, since friction always resists motion, you kind of tack that on in the end. So you want to find this one. It's like, this one will tell you, actually, you know what? You don't even need to find this. Who cares? Who cares the direction it's actually going? You're going to take this, when you're talking about the F net, you take this, make it positive, because who cares? And then you subtract the force of friction that's on this block, so that you'll calculate that with m2g cosine of theta times mu, and that'll have to be the kinetic friction. Since this always opposes the force of the direction of motion, it doesn't really matter in which direction you're going. What's that? So after you do all of that, so the absolute value of the difference between the forces, and then you subtract the force of friction, you're going to take the F net, and you're going to divide it by the total mass. And that's your acceleration. Yeah, the adding the friction seems like it's going to make it trickier. Um, but it just, kind of doesn't, since it always resists the force, like it resists the direction of motion. So it doesn't really matter where the thing is going. You just calculate the force of friction on that block that's on the ramp and subtract it from the normal net force, and then you get a new net force divided by the combined mass, and that's your acceleration. Hello, whoever's new. Well, that's a shame for whoever stopped in. The viewers are happy. But I'm just tired. Well, I'm glad I could give you like an hour and a half of private tutoring. Uh, it was open for, of course, other people, but I'm glad at least someone showed up. No problem. Uh, see you tomorrow. Hmm. But yeah, thanks for joining me and Arthur. I guess I'm gonna shut it down because it doesn't look like we have any more takers tonight. Uh, so yeah, see you tomorrow and have a good night.